Hello, my name is Šimon Tóth. Thank you for choosing my talk. Today's talk is inspired by the many package-oriented talks that were presented at recent conferences. And I should say, most of these talks are great and you should definitely watch them. However, many of these talks share a common undertone of being dismissive of monorepo setups. My personal philosophy is that you should use the right tool for the job. And therefore, here I am trying to balance out the negative marketing. In the first part of the talk, I will go over the main differences between monorepo and polyrepo setups. And then, the majority of the talk will be spent going over different use cases of Bazel as the build system for a monorepo environment. I encourage you to follow along for the second part of the talk, and to do that easily, I have prepared for you a dev container environment. All you need is Visual Studio Code and Docker on your machine. Then simply open the repository in Visual Studio Code, and you should get an on-demand built Docker image that you can use to follow along for the second part of the talk. Before I start with the first part though, I need to do the mandatory self-plug. I have a free book about C++ algorithms. You can grab it on GitHub, or if you also want to donate to EFF, it's also available on NinPub. Besides that, I also post daily C++ content on Twitter and LinkedIn. With that out of the way, let's start with the talk proper and let's have a look at the differences between monorepo and polyrepo environments. So what is the difference between a monorepo and a polyrepo? Well, the prefix mono means one or single, and the prefix poly means many. And I could stop there, but I won't. First, clearly, this is a spectrum. If you have two big repositories with many projects each, do you really have two monorepositories, or do you simply have a polyrepo? In this talk, I will be discussing mainly the two extremes, that is, everything in a single repository, or each project in its own repository. And notably, this is already fuzzy enough since I didn't specify what I mean by a project. On top of that, a clear delineation isn't really that important, especially not in this talk, because there is a second and arguably much more important axis. First, we have the ad-head model, where we build everything from the current sources. In the extreme cases, you could even build your operating system, your compiler, and all the tooling from sources. For practical purposes, there will generally be some sort of cutoff between what you consider the platform that you build on top of, and what you consider to be your project that you build from sources. The second model is the binary model, where everything is a version binary. For both of these models, we will need some sort of infrastructural support. For the ad-head model, we will need a build system that will only rebuild what is absolutely necessary for each change. For the binary model, we will need a package manager that is capable of resolving version requirements into a single cohesive release. Now, I said that the distinction between monorepo and polyrepo isn't that important for this talk, and that is because I will be only talking about two specific combinations, specifically the ad-head monorepo and the binary polyrepo. Technically, the other two combinations are possible, but I consider them strange choices. However, if you actually use either a binary monorepo or an ad-head polyrepo, I would love to hear from you. Please get in touch. A lot has been written about these two models, so I'll be fairly brief, but I do need to give you some sort of introduction and point out the core differences. Let's start with the pain points. For the ad-head monorepo, the main pain point is scalability. If you don't have a suitable build system and don't structure your project appropriately, you can easily end up in a situation where you will have large parts of your project being rebuilt every time for every change. This can become very quickly infeasible. For the binary polyrepo, the main pain point is ABI stability. Since the different projects interface with each other using binary artifacts, you either need ABI stability Or if you don't, then you actually end up in the same situation as before with the monorepo, and you need to rebuild everything all the time. The big benefit of monorepo is that we maintain the ability to do global changes. Since all the code is in a single place, we can actually do operations like upgrading the version of the compiler or doing a global refactoring. Just to be clear, I'm definitely not claiming that these operations are easy. If you want to see how incredibly hard such operations actually are, I do recommend that you watch some of the talks from Google, notably the talks about switching from unordered map to flat hash map, and more recent one, switching from uint64 to uint64_t. But while not easy, these operations are at least possible. With the binary polyrepo, we effectively disallow global operations completely. Each project is its own isolated bubble. So we really need to step outside of the system to reintroduce any sort of global coordination. In practical terms, there will be a lot of this coordination and possibly some top-down company mandates. The two models also differ in how they handle dependencies. Private dependencies, that is, dependencies that you do not expose through a public interface, can be problematic with the hat model. This arguably depends on how exactly you manage multiple versions of the same dependency. Generally speaking, in a monorepo, you would only have one copy of a dependency. Well, if you have one copy of a dependency, well then even if a dependency is private for you, it can still be potentially shared with other teams, meaning that it's effectively shared. If you allow multiple versions, then private dependencies are trivial. With the binary polyrepo model, private dependencies are just that. They are private. Because each project is isolated, changes are completely local as long as you do not leak the dependency from your public interface. Shared dependencies are a bit different. They need to be carefully managed in both models. In the monorepo, the shared dependency can introduce breaking changes in other parts of the repository. The good thing is we have global operations, meaning that if the change is breaking, well, we will know immediately, and the person making the change still has enough context, hopefully, to make a trivial fix. On the other hand, in the binary polyrepo, the situation is more complicated. First, we must ensure ABI stability. Well, if we have a shared dependency, meaning something we export through our public interface, well, that's part of our public interface. So any ABI change is a problem. Second, if the change is breaking, it might not be noticed for quite some time. Version upgrades are not necessarily under the control of the provider of the dependency. And to some degree, it can also matter what kind of dependency resolution algorithm you are using. Because of this disconnect, a breaking change might be noticed after a long time, which might mean that there will be additional triage time on the side of the user, and when the fix is actually required, the local context might be already lost. To be clear, on the whole, these two models are equally good. The point I'm trying to make here is that they might not be equally good for you, your company, or your environment. I want to close this section of the talk with 3 more points that are a bit more abstract. The monorepo very much requires a cooperative environment. If you make a change and accidentally break a user, well, you will know immediately, and you actually do need their cooperation to move forward. In the binary polyrepo model, can actually work in a competitive environment. If you are dealing with breakages outside of the documented behavior, well, then it's generally the problem of the user, and the user will have to deal with that. The monorepo also implies a conforming environment. Since all the code is in one repository, this implies common tooling, common code style, processes, and so on. With the binary polyrepo, well, each project can have its own tooling and style. As a consequence, there is a definite bias in these two models. In the add monorepo, it is the users of dependencies that have the easier time. And in the binary polyrepo, it's the providers of dependencies that have the easier time. So do choose carefully. I did mention that both the add and binary model will require special tooling. So let's switch gears and let's talk about the Bazel build system. Bazel is an open source build system which originated from Blaze, the build system used in the Google Monorepo. This heritage is what makes Bazel great as a build system for monorepo environments. I have debated how exactly to structure the practical part of this talk, and ultimately I have settled on a series of recipes that should give you a good idea of how Bazel works and also give you a good starting point if you want to explore these areas further. And naturally, we have to start with a hello world. To compile this simple program, we must first set up our Bazel project. And to start with that, we need Bazel itself. If you are following along, the Docker image already comes preset up with Basilisk. Basilisk is a tool that will automatically download the requested version of Bazel and then behave as the Bazel binary. In the Docker image, Basilisk is already symlinked, and in the root of the project, we have a Basilisk RC file, which specifies the version of Bazel. To verify, we can query the version of Bazel. Moving on to the actual project, we need one mandatory file, the workspace file. For now, we can leave it empty or specify the project's name, although do note that since all the examples I will be showing in the talk are in a single monorepo, the workspace file already has additional configuration that I will be talking about later. The second project-wide file is Bazel RC. Here we can specify the command line arguments for Bazel. This is typical the place where you configure project-wide settings. For now, we will use it to set up our compiler and flags. Finally, we need to tell Bazel how to actually build our Hello World project. This is done through the build files. For our Hello World, this is very simple. We have one source file, and the only other thing we need to specify is the name of the resulting binary. With this, we can now build and run our Hello World program. You might have noticed that I use a special syntax to refer to the Hello World binary. So let's take a short detour and talk about how Bazel organizes packages and targets. Whenever we refer to a target, there are three components of the full path: the repository, the package, and the target itself. Note that the package path corresponds to the file system path. To refer to a local repository, we can use the @ sign without any name or skip the repository part altogether. Similarly, when we refer to local targets, we can skip the package path. On the other hand, when the target name matches the name of the package, we can also skip the target name and use the package path only. To demonstrate this behavior, let's go back to our code. If we switch to the directory with our Hello World program, we can use the target name only. I have also prepared a copy of the Hello World program in a subdirectory. We can again run this binary using the full path. Or since in this case the name of the target is the same as the name of the package, we can omit the target. A simple example like this is great for demonstrating how to build and run binaries. However, your project is probably more complex. So let's split the Hello World program into several pieces. The Hello World main now delegates to a library to print a greeting. This is then reflected in our build file, where the binary route depends on another target. As already mentioned, the package naming matches up with the directory structure. So let's have a look at the greeter directory and let's explore the library. The greeter delegates further to a formatting library to format the message. The message itself is also stored in a separate header. To build the greeter library, we will require now a more complex build rule. First, the formatting library remains relatively simple. However, note that instead of cc binary for binary, we now use a cc library for a library. For libraries, we also have an additional attribute specifying the public headers. In this case, we have only one source file and one public header. The greeter library takes advantage of multiple features. First, we take advantage of private headers. Headers that are not listed as public will not be accessible to the user. In this case, the greeter dev header will not be accessible to our hello world binary. Second, we also take advantage of implementation dependencies. These are non-transitive dependencies that again won't be available to the user. Here we declare the format library as a non-transitive dependency. Finally, we are specifying visibility. By default, each target will be only visible within its own package. If we want to make a target accessible from other packages, we need to change its visibility. Here we mark the visibility as public, meaning that this target will be accessible from any package. Besides private and public, the visibility rules offer fine-grained control, but this is not something I'll be going over in this talk. Building our hello world now involves building the greeter and format library, but this will be handled for us transparently by Bazel. I talked about the private headers and implementation dependencies, so let's quickly have a look at what happens when we include the private header or rely on an implementation dependency. First, let's have a look at the binary that includes a private header. When we try to compile this program, we will receive a warning, and because I have warnings set to errors, this program will fail to compile. Second, let's have a look at the binary that includes a public header, but from an implementation dependency. When we try to compile this program, the public header from an implementation dependency will simply not be accessible. Both private headers and implementation dependencies are features that are not enabled by default. Therefore, we need to go to our Bazel RC file and add these as runtime flags to the build command. On top of that, private headers require compiler support, so they will only work with the client compiler. Our examples are starting to grow in complexity, so it's the proper time to start talking about testing. Testing frameworks are external dependencies. So if we want to start testing, we first need to discuss how to pull an external dependency into our Bazel project. I will be using the Google Test and the Catch2 frameworks to demonstrate. Both of these already support Bazel, which makes the situation simpler. All we need to do is to load the dependency into our project. However, there is a distinction. Google Test already supports the new Bazel module functionality, which Catch2 doesn't. The benefit of Bazel modules is what you would expect. They resolve the correct version of transitive dependencies to satisfy all the requested modules. When importing a dependency manually, we might need to take care of some of the transitive dependencies. Modules are added into the module.bazel file. So for example, here we are pulling in the Google testing framework and one of the transitive dependencies for the Catch2 framework. To import a dependency manually, we need to go to our workspace file. Here we use the HTTP archive rule, which is the recommended approach. However, you can also use the slower route and pull using the Git protocol. The typical naming schema for dependencies is the domain in the reverse order, and for GitHub, the user then followed by the repository name. Since the naming is purely for the purposes of this project, we can of course choose any name that is convenient. Now that we have our two testing frameworks ready, it's time to write some tests. The C++ code isn't essential here, so let's skip directly to the Bazel configuration. On the most basic level, a test is simply an executable that either returns a 0 for success or a non-zero value for failure. So it's not that surprising that the definition for a test is similar to binary. The typical naming convention for a test is the dependency being tested followed by an underscore test. Besides the sources, we also need to specify our dependency, which at minimum will be the testing frameworks and the dependency we are testing. In this case, we depend on the Google testing framework. And despite using a different approach for pulling in the dependency, the same test using the Catch2 framework will look almost identical. I did not explain the size label yet. By default, the only thing that is affected is the timeout for the test. However, this information is also provided for the test binary, so if you are providing custom main for your tests, you can do extra things, for example, enforce different system limits based on each of the supported sizes. I said before that the test is simply a binary that either returns 0 on success or a non-zero value on a failure. We can combine this with the fact that Bazel supports multiple languages and write a simple black box test. Here we have a rule for a shell script that we use as a black box test. We still have the same structure. We have a name for the target, we declare our sources, but we have one distinction. We do not depend on our C++ code using a code dependency. Instead, we pass it in as a data dependency. The distinction is simply that code dependencies have semantic meaning. This meaning is built into the rules. For example, the C++ rules understand that if we are depending on a library, that library needs to be linked in to the binary, and the public headers need to be made available during the compilation. Data dependency is still treated as a dependency within the Bazel framework itself. So for example, if we would change the binary.cc here and then run the black box test, the binary will be rebuilt, so the test is running against the current version. But there is no other implied behavior. However, we do have a slight problem. Bazel is a hermetic build system. One of the consequences of that is that tests do not have access to the normal file system. And each run of the test might end up with unique paths on the dependent data. Therefore, what we need to do is pass in the current location of the tested binary. One of the ways to do that is to pass the location as an argument. I should note that while I have picked the shell script as the language here, the same approach can be used to write external tests using Python or even JavaScript. The complication created by hermetic execution is something that you will run into even with C++. Fortunately for C++, Bazel also provides a helper library that can translate the paths from workspace to runtime. So let's have a look at an example. Here we have a simple test that has a data dependency on file.txt. We also depend on the Bazel library that provides this runtime support. Inside our test, we can then use the runfiles library to translate the workspace path to our data to the current file path. Finally, I should quickly note how we can run our tests. Perhaps not unexpectedly, we use the Bazel test command, and as we have seen previously, we can point it at a single target. However, more typically, what you want to do is run all tests in a particular package. For this, we can use a shorthand. The 3 dots represents all targets in the package and all its sub-packages. You might also notice the cached annotation for the test that we ran previously. This is because Bazel employs cache even for tests, meaning that it will only rerun tests that were affected by changes. Once we have testing coverage, it's also worth turning on sanitizers. Sanitizers can run on top of already existing tests and catch subtle bugs that wouldn't be manifesting otherwise. The way to integrate sanitizers into a Bazel project is through configurations. Let's switch to our Bazel RC file. So far, all the flags we have added were applied globally. Configurations allow flags to be grouped under a configuration label, and then these are only applied when that configuration is requested. For example, here we add flags for the address sanitizer. That is the compilation flags and the linker flags all under the ASAN configuration. The platform suffix is required to ensure that we don't trample over our non-ASAN cache. We can then use this configuration by passing the config ASAN to a test or run command. Since we just talked about sanitizers, it's only fair to discuss static analyzers. Because most static analyzers rely on a compilation database, we can integrate static analyzers externally by having Bazel emit this database. To do that, we can import the third-party module, and as with previous external dependencies that don't support Bazel modules yet, we add it to our workspace file. This particular module provides an executable that will generate the compilation database, so all we have to do is to simply run it. Alternatively, if you want to integrate a specific static analyzer, for example clang-tidy, we can opt for a more integrated solution that can take advantage of Bazel caching facilities. Again, this is through a third-party module. We can invoke this module manually, however the optimal approach is to integrate it using another configuration for the build command. The specific flags are simply copied from the documentation of the module. With this done, we can now build targets and have clang-tidy automatically run with the build. Here we have an example which doesn't report any issues, and another example that does. For the most part, we have a complete project now. I talked about how to structure your code, how to pull in external dependencies, how to write tests, and how to use sanitizer and static analyzers. So far, I have made life very easy for myself. We are building for one specific platform. Not to mention that I simplified things even further by just building inside of the tightly controlled Docker image. Well, building inside of the Docker image makes sense. You will probably need to build for several platforms, and that usually means dealing with some of the idiosyncrasies of the different platforms through platform-specific code. To handle platform-specific code, we need two Bazel features: platforms and constraints. However, for C++, we first need to flip a flag in our Bazel RC, since the introduction of platforms and constraints was a breaking change. Bazel already comes with predefined labels that describe the common CPU architectures and operating systems. And the simplest way to integrate with these is to mark specific targets as platform-specific. This is particularly useful for tests. In this example, we mark this particular test as Windows only, which means that if we try to run tests in this package, this test will not be run and instead it will be skipped. Having platform-specific code not cause issues on platforms where it's not supported is one thing. However, for a project to fully support multiple platforms, we will probably need platform-specific dependencies. As an example, let's take this simple program that prints the platform information from a library. This binary then pairs with the specific libraries, one for Windows and one for Linux. Now we just need to put this together in our build file. First, we constrain our platform-specific libraries to the corresponding platform to make sure that they do not cause any accidental build or testing errors. Then, on our multi-platform binary, we use a select rule to pick the correct dependency based on the platform. When we run the resulting binary, we get the Linux version, since we are inside of a Docker image that is Ubuntu-based. I should note that while I'm demonstrating platform's feature on a predefined constraint, you can absolutely define your own. If you, for example, need to introduce a bridge library to deal with an old version of a dependency, you can introduce the version of the dependency as a platform feature and then use the select logic based on the version information. The complementary part to platforms are toolchains. Typically, you wouldn't really define your own toolchain, but instead use platforms to constrain your targets and define the target platforms, and let the language rules figure out what toolchains are appropriate. However, C++ is a bit special. For C++, it's often desirable to build a project using multiple compilers on the same platform. And to do that in a controlled manner, you would have to define custom toolchains. I will not be showing an example of that here, because it's a highly mechanical process, but if you are interested, Bazel has a very good tutorial on how to define a custom C++ toolchain. Instead, let's have a look at something more practical, cross-compiling into WebAssembly using mscripten. First, as before, we need to pull in the module for mscripten. The mscripten Bazel module defines the required mscripten toolchains that can then cross-compile C++ code into WebAssembly. To demonstrate, let's take this Hello World program. The C++ side of things is the same as before. We simply have a CC binary with one source file. The WebAssembly toolchains are packaged into build rules that use the WASM prefix. Therefore, to cross-compile our Hello World, we need to create a new WASM binary and pass our C++ target as one of the attributes. Once we build it, we will get the expected WebAssembly files in the Bazel bin directory, and we can run the resulting JavaScript through Node. So far, I haven't really discussed these symlinked directories that Bazel creates. These point to different parts of the Bazel cache. For example, the Bazel bin for binaries and Bazel out for generated files. While we could pull out binaries out of the Bazel bin directory and pull out the generated files out of the Bazel out directory manually and then package them, that would be inherently quite brittle and, of course, unnecessarily complex. So let's have a quick look at how we can package our project using Bazel itself. I will be demonstrating using a Debian package. For other artifacts such as Docker images or Windows installers, you will need different Bazel modules, but the overall approach is the same. Let's start with a simple program that reads and prints the content of a file installed in the user share directory. First, we need to package the binary, in this case using the package star rule. The combination of the strip prefix and package dir means that the custom command binary will end up directly in user bin. Second, we need our file. This is the first time I'm showing the file group rule, and it's exactly that, meaning it's a group of files that we can then refer to under the new label. We then package this data, ensuring that the file ends up in the correct directory. Finally, we put this together, wrap everything as a Debian package, and add the required metadata. When we build the package, Bazel will take care of building all the dependencies, and at the end we end up with the Debian package that we can install. Once installed, we can run it from the system location. When I started this talk, I mentioned that to make the Red Monorepo model feasible, we do need a build system that only rebuilds what is absolutely necessary. And Bazel ensures that through caching. However, what happens if you are in a multi-developer environment? Can you still take advantage of caching? Let's start with GitHub. To ensure that we are not rebuilding everything all the time and not rerunning tests that do not need to be rerun, what we need to do is store the cache in between the runs. Fortunately, to do that, Bazel already provides a cache action. We can use this action to store the cache in between runs. The GitHub action itself is fairly minimal. We check out our project, we fetch the previous cache, install compiler and Basilisk. However, please know that I'm really only doing this from pure laziness. The proper way to do it would be to build a Docker image with these already pre-installed. This way we are really wasting a lot of CPU cycles on the installation. Finally, we can run the tests. After pushing this configuration to our repository, GitHub will now test each commit, but more importantly, it will keep the cache in between the runs. I can demonstrate by updating the project with a dummy file. We can then check that both of the tests were skipped, since they both still have a valid cache state. Alternatively, if you are using a local build environment, you can take advantage of remote caching. I will demonstrate an approach using WebDev. However, there are other options also available. First, I have a small script that just sets up Nginx as the WebDev server and starts it. Once this is done, we can turn on remote caching in our Bazel RC file, and then populate the cache. To demonstrate that the cache is working, we can switch the cache to read-only. And now if we clear our local cache and rerun the command, the tests are still cached, because they were fetched from the remote cache. For practical setups, you will generally want only your continuous integration to write into the cache, and have all developers only read from the cache. This means that if they pull a fresh version of the project, that code was already compiled and tested by the continuous integration, and therefore is already in the cache. At the same time, any local development will not be able to poison the cache. Finally, I want to close this talk with a couple of topics that are worth mentioning, but did not make the cut for the full demo. What about Windows support? Well, sadly, Windows platform is not really my area of expertise. However, as I understand it, Bazel should work just fine on Windows and should interface with the Microsoft toolchain without any problems. Throughout the talk, I have used quite a few bleeding-edge features. Not to mention the fact that the Docker image is actually running a pre-release version of Bazel. Now, this makes complete sense for a conference talk, but what about production? First, you should absolutely use a stable version of Bazel. The stability of the experimental features is mostly fine, however there are many corner cases, in particular when multiple features interact. There is a very good reason why the examples in the talk are separated by feature. Adding third-party modules into the mix makes everything even more brittle. As I was preparing for the talk, I actually did report quite a few bugs both to Bazel and to the third-party modules. Talking about the third-party modules, you might have noticed that I used quite a few of them. And to be fair, this is actually the typical Bazel experience. The reason why this is because Bazel is written in Skylark, which is a subset of Python, and as a result, writing modules is fairly easy. Hence, most things that you might want were already implemented by someone else. If you want to write your own module, Bazel documentation is also quite good. Since we are talking about modules, what about C++20 modules? Well, there are two third-party modules that provide C++20 support. Unfortunately, one of them is relying on the Clang pre-C++20 module implementation, and the second module is right now transitioning to Bazel modules and does not work. On top of that, there are still a couple of compiler issues, notably Clang is still hard-coding paths inside of the compiled modules, which is effectively breaking the Bazel hermetic build model, because Bazel is building the paths end up being effectively random. I have also silently avoided third-party C++ dependencies in this talk. Now, the thing is, you have a couple of options how to pull in third-party dependencies, C++ dependencies. Notably, there is a third-party module, foreign rules, that's maintained by the Bazel team, which can actually wrap external build systems. However, if the project is doing anything strange or custom, it quickly runs into issues. You can also opt into an approach using package managers. If your package manager supports Bazel, well, then you can pull in the dependency as a binary and use the package manager integration into Bazel. And the third is the most painful one, which is where you pull the project in using simply the HTTP rule to just download it into your project and provide a manually written build file. I have also talked a lot about caching and cache tests, but sometimes tests simply run too long or can't easily be switched to a hermetic mode. So what do you do then? Well, unfortunately, then you will need to partition your tests. You will need a group of tests that can run with each commit and a group of tests that run after the code has been already committed, potentially not on every commit. If the code passes through the initial test but fails on the integration test, you might need to do git bisect to figure out the specific commit responsible. And I would recommend the policy revert now and ask questions later when you find the commit responsible, and just punt it to the author to figure out what actually happened. Finally, I have also included quite a lot of links and references in the talks repository. So I invite you to browse through them so you can also live comfortably at hat with Bazel. Thank you.